Number one, we're going to compute a limit of a couple of functions. Now, as I mentioned in class, it's easier to show that the limit doesn't exist than to prove that it does. So I'm going to cook up one where the limit does exist and show you the process. So the limit as x, y approaches 0, 0 now, so if you try the usual approaches for figuring out if a limit might exist, for instance, you set y equal to mx for some m and see what happens, that suggests that the limit is going to be equal to 0. So the idea is, the problem is how to prove that. So what you do is you try to bound the function, you try to bound the difference between function and whatever value we think is the limit in terms of the distance between x and y and the point we're approaching. So here we have f of x minus f of xy rather minus L in terms of x, y. So we try to bound this in terms of this. That's the general approach. So how can we do that? So first, let's break this up into two separate fractions. Okay. Now, the second one is actually the easier one to work with, so I'll show you that first. Factor out an x up top. And then we have y to the fourth over x to the fourth plus y to the fourth. And the idea is this fraction here, y to the fourth over x to the fourth plus y to the fourth, can be bounded. So it's actually, so this is greater than or equal to 0, less than or equal to 1. And what's really important here is that all the exponents here are even. So everything we're talking about here is non-negative. Yeah, so if there were negatives involved here, then the picture would be a lot more complicated. We couldn't really do anything.
How does it prove that it's less than or equal to 1 though?
Since y to the fourth is going to be...
The denominator is bigger than the numerator.
Exactly, yeah.
Okay.
It has to be. Alright, so what that means is, so this whole term has to go to 0 as x and y go to 0. Because you have this x sitting here. So right now we don't care so much about that, but the fact that at least this whole term is less than or equal to the absolute value of x. Now what about the other term? This one right here. We'd like to bound this in a similar way. So there's some way we can pick it apart a little bit and come up with things that we know are less than or equal to 1. It's a little trickier than this. Now we've done things like this in some examples in class, that was a long time ago, where we had expressions like this. For instance, we had, x over square root of x squared plus y squared. We know that this is less than or equal to 1. So if a powers match, here we have x to the first, and then we have x squared, but it's a square root. So, and the denominator is, again, it's going to be bigger than the numerator. So we know that's got to be less than or equal to 1. So if we look for expressions that are kind of like this, then we can figure out what to do with this to identify pieces that are going to be definitely less than or equal to 1. So now if we write it that way, oops, that's x. Alright, then what can we do with it? Yes, sir, we have even exponents, but the powers don't quite match up.
Couldn't you just simply say that that it's bounded less than 1 because the denominator has to be larger than the numerator since all of our terms are positive?
The trouble is you have to worry about whether x is less than 1 or greater than 1, and that changes the picture.
Okay.
Yeah, here we can say this is true no matter what x is. These powers are ones that are too big. Some of these y's can actually help you out here. And I'm going to break the denominator up. So we have, just to write it a little differently, y cubed over this guy, x squared over this guy. Alright, now what can we do? This part is less than or equal to 1. Over here. Yeah, it's bounded by the absolute value of y. So I'll rewrite this as y times y squared. So now the shoe's on the other foot. So this is less than or equal to the absolute value of y. And we can break this up in whichever way we need to in order to distribute this around and get the kind of bound that we want. So now what we have, let's put it all together. So the entire thing we started with y to the fourth over x to the fourth plus y to the fourth is less than or equal to, the first part was less than or equal to the absolute value of y. The second part was less than the absolute value of x. Now either one of these is less than or equal to square root of x squared plus y squared. So the whole thing is less than or equal to, just being really conservative here, 2 square root of x squared plus y squared.
Why is that the absolute value of y?
What if y is negative? Then, if y is negative, this part, let's suppose it's actually less than 1, then what we have here is going to be actually greater than or equal to y, because it's going to be less negative than y is. But if we say absolute value, then we know we're covered. So if this is less than or equal to 2 times the square root of x squared plus y squared, that means we can choose delta epsilon definition of a limit, delta, to be equal to epsilon over 2. So this whole thing, we want to be bounded by some function of x squared plus y squared. So whatever function we get, in this case multiplying by 2, we do the inverse over here.
Where did that 2 come from?
Oh, because each one of these individually is bounded by square root of x squared plus y squared.
Okay, so
So to get yeah, and I don't mind if a bound is a bit conservative.
Can you explain that a little more?
Okay, so absolute value of y is less than or equal to x squared plus y squared. So is x, absolute value is equal to the square root of x squared. But since I got to sum of these things, I got to add these as well. So that's where the 2 comes from. So now, let me say the general principle first. If the difference between the function and what you think is a limit, if you show it is bounded by some function g of the square root of x squared plus y squared, g is a 1-to-1 function, certainly multiplying by 2 is, and it needs to be increasing. Then you can choose epsilon to be equal to the inverse function, so in this case dividing by 2. Sorry, delta is equal to g inverse of epsilon. So for instance, if what you got here was x squared plus y squared, then g would be the squaring function, and you take delta to be the square root of epsilon. To wrap it up, what you do is, using the definition of a limit, you let epsilon be greater than 0. So, say if x squared plus y squared is less than delta, then f of xy minus L, which you already established is less than or equal to square root, well, for whatever you got, so in this case, 2 square root of x squared plus y squared. But this square root of x squared plus y squared is less than delta. So, it must be less than g of g inverse of epsilon. These cancel out, and you get epsilon. So, applying this to what we have in this specific problem, you have x squared y cubed plus xy to the 4 over x to the 4 plus y to the 4 is less than 2 square root of x squared plus y squared. But this is less than delta, which is equal to epsilon over 2, because that's how it was chosen earlier. So this whole thing must be less than 2 epsilon over 2, so it must be less than epsilon, therefore the limit actually does equal 0. So the other most painful problems on this exam, 5 and 10, involve this definition too.
Alright.
Okay.
The g squared root of x squared plus y squared, how can you say that that's less than g inverse g epsilon?
Okay, because you're assuming that x squared plus y squared is less than delta, and you've defined delta to be g inverse epsilon. And this is where it's important that g is an increasing function. Otherwise, because if the function is increasing, that means that x is less than y implies g of x is less than g of y, and it also implies g inverse of x is less than g inverse of y. So that's what allows you to make that leap. But the functions you're going to get for g tend to be very simple, like multiplying by a constant, or squaring, or raising to some other power, something like that, that's easy to invert. You're trying to relate the distance between y values to the distance between x values. If you show that they both go to 0 together, and that's what this does, then the limit is happening. Doing this example, a function like this, on the other hand, you think you could do the same thing with this kind of function? If the powers up top are greater than the powers on the bottom, this actually fails, the limit doesn't exist, because of this denominator becoming 0 when x is equal to minus 4y, then you can try this process, but it'll fail. If you try this, that's when you'll find it fails. Showing that a function is differentiable using the definition. So what I'll do, same thing, I'll step through a similar one. So the problem I'll do to illustrate is this. Show is differentiable at this point, 1, 1.
This number 5.
So the idea is this. You compute LF of xy, which is the linearization, which you had to do in number 3 of f, at this point, x naught, y naught. So I won't go through the process of actually computing at